So today we are going to be talking about, actually, a better way to put this is we're going to begin talking about what happens when we use an AC signal to excite our magnetic circuit. So very briefly, we're going to review ferromagnetism. Then we are going to talk about losses in our cores, which only occur when there's a time varying flux flowing through them. And then we're going to work a problem and then we'll be done. And then that's going to kick us off into talking about induced currents and voltages, which will be our introduction to transformers for Thursday. So we have talked very briefly about the concept of ferromagnetism in this class. We said that ferromagnetic materials include certain forms of iron and its alloys in combination with cobalt, nickel, aluminum, and tungsten. So let's write that down again. So ferromagnetic materials. Include iron and its alloys. In combination with cobalt. Full aluminum and tungsten. They are characterized by their high relative permeabilities. Where we learned already that mu r, the relative permeability of a ferromagnetic material, will be much, much greater than 1. And earlier on, we also said that a high permeability effectively meant that it was easy to magnetize these materials. So now we're going to talk about what that ease of magnetization really means. Okay. So I'm going to draw a picture here. And I'm going to make 3 copies of it so that we can talk about different things. So this box here is supposed to be representative of a ferromagnetic core material. And it's going to be representative of that material prior to magnetization. Okay, so what I'm drawing right now are what are called Weiss domains. And it's not remotely important that your domains look like my domains at all, since these are supposed to just be randomly oriented grains in the material. So just attempting to draw a bunch of weird, funny looking shapes here. Like so, and now I am going to make a copy of this shape. And I am going to paste it on my screen a couple of times as we talk about the magnetization process. All right, so our leftmost picture is going to be before our material is magnetized. I want to say I've been using this light blue thing for my magnetic field lines, so that's what I'm going to continue to illustrate here. So we have these Weiss domains in our material, and each of those Weiss domains has all of their atoms aligned such that there is a net magnetic field in one direction. So let's say, just for the sake of argument, that this domain here has a magnetic field that's directed to the right. This one has one that's directed down. We have one diagonally down like so, one diagonally to the right like so, up and to the left like so, up like so, to the right like so, diagonally down and to the left, another one down and to the left, one up and to the right, and one down and to the right, like so. So what I've tried to illustrate here is that the magnetic field directions in all of these domains are effectively random. And if we added them all up together, it would be roughly 0. So we should not see that any net magnetic flux passes through this unmagnetized material. All of the small pieces of flux from each one of these domains cancels each other out in some form. So any net flux we would see would be incredibly small, if not almost exactly 0. Okay. Now, if we were if we were to subject our high permeability core material to an external magnetic field, we would magnetize our core. So this is what it's going to look like during magnetization. And here I'm going to assume that my applied field is in the right direction. So effectively, we should see that everything that was kind of to the right is more aligned to the right. Like so, and everything that was aligned not to the right has effectively started to turn towards the right. Like so. Okay. And then finally, on the right-hand side, we will have what I'm going to call saturation. Okay. So let's talk a little bit more about the magnetization process. Okay. So we have passed some current through our coil and we are generating an H field measured in amps per meter that is trying to align our domains all in the same direction. Okay. So as that H field gets more and more strong, our B fields inside of our material become more and more aligned, right? Now, there's going to be a certain point at which we can't align the domains any more than they already are. If they're all directed to the right, if we increase the current in our coil, therefore increasing H, we're not going to see a corresponding increase in B because the field can't be any more directed exactly to the right. So that's what saturation is going to look like. All of our field lines are going to be directed to the right in the exact same direction. And we call it saturation because an increase in H field does not yield a corresponding increase in B field. Okay. So we can characterize this process using what's called a magnetization curve or a BH curve. So I'm going to draw a simple little picture here. On the vertical axis is our magnetic flux density B, measured in Tesla. On the horizontal axis is our magnetic field strength, H, or our magnetization force, also H, measured in amp turns per meter. And what we're going to get is a curve that looks something like this. Let me draw this again where it's not so damn wiggly. So this curve has three distinct regions. Let's start with this guy right here. So this is our linear region. And to this point, we have assumed that all of our devices have been operating in this range. Here we have our knee region. So this is where our BH relationship becomes nonlinear. Okay. And then finally, we have our saturation region, where increasing H doesn't cause a change in B. Okay. So the handout that I gave you guys has the magnetization or BH curves for a couple of different materials. So on the front of it, we have a magnetization curve 1929 gauge steel and a soft steel casting for magnetizing intensities ranging from roughly 0 amp turns per meter all the way up to 8,000 amp turns per meter, and magnetic flux densities ranging from approximately 0.2 Tesla all the way up to 2 Tesla. On the back of the sheet, we have another set of curves from a different textbook for a few more materials. Cast iron, soft cast steel, silicon sheet steel, and a nickel iron alloy. And they all behave roughly like this. It's just to relative degrees, okay? So to this point, we have described what would happen if we were to use a DC current. Now let's talk about what happens if we were to use an AC current, okay? So let me write on here really quickly. Magnetization or BH curve for DC currents. We're going to have something similar-ish for AC currents. Since our current can change direction, we need to look at all 4 quadrants of our graph. So this is going to be our H-axis. This is going to be our B-axis. Once again, B is measured in Tesla, and H is measured in amp turns per meter. Okay. So if we had an AC current, it is creating some time varying external field. And so we see a time varying flux flow through our core material. So as our current increases, sorry, let me draw this better. As our current increases, we're going to get something akin to our normal magnetization curve, right? So our current is increasing, and as we keep applying more and more H, we eventually saturate. Now, what happens as we start to decrease our current? Well, our material will start to become, let me call this the origin point 0 and this point right here, A, okay? So from 0 to A, we have normal magnetization. When we start to decrease our current, what we're going to see is something that looks like this. So let's call this point B, okay? So effectively, when we turn our H field off or turn our current off, we can observe that there is some residual flux density in our core material, where the magnitude of that residual flux density is the height of point B above the horizontal axis. So this is residual flux density, B residual, like so. So what does it mean that we have some residual flux density? Anybody have any ideas? The material is still magnetized. So effectively, we have turned a raw magnetic material into a permanent magnet. This is literally how you magnetize materials in industry. You put it in the presence of an electromagnet, drive it into saturation, and then turn your current down, and it retains some amount of residual magnetism. Therefore, your device behaves like a permanent magnet. If you wanted to try something like this at home, Google it so that you do it safely, but you can make a simple electromagnet simply by wrapping a coil around a wire, or excuse me, wrapping a coil around a nail, passing a current through the coil, and then you'll see that the nail still remains magnetized to some degree. Okay. Assuming the nail is made of some sort of steel material. Okay. All right, so as we continue to, or we've returned our current to zero, so now let's see what happens if we change the direction of the current. So changing the direction of the current, oh, sorry, let me go back to the right color here, is going to continue to demagnetize our material until we reach point C here, where we have no residual flux density. Okay. So this is going to be called, this level of H is negative H sub C, where this is what we're going to call a coercive field, because it has coerced or forced the magnetization of the material back down to being unmagnetized. Okay. As we continue to pass current in the opposite direction, we're going to get to point D over here, in which case we've hit saturation again. So we can only align the domains so much in the opposite direction before they can't be any more parallel with our field. And then we increase the current like so. So we have some residual flux density in the opposite direction. So effectively, if our north pole of our permanent magnet was on top, now the north pole is on bottom. And then we keep on keeping on like so. And this process just repeats itself over and over and over again. So this is an AC magnetization curve. Also commonly known as a hysteresis loop. So this hysteresis illustrates a very interesting and important quality of ferromagnetic materials. They have memory in the presence of AC excitation, okay? What I mean by that is their current level of magnetization depends on how they were magnetized in the past. This is literally how old magnetic storage material like floppy disks and tapes, magnetic tapes, like used in cassette tapes, VCRs, 8-tracks, and all that kind of stuff, literally how they work. You magnetize them to some certain amount. in some certain region, and that is considered an on state. If it's not magnetized, it's an off state, and that's how you get your binary ones and zeros that were interpreted by computers. Now we use effectively the states of transistors and all that kind of stuff to do the same thing, but back in the day, it was all magnets, okay? Which is why you can't store any of your old magnetic media in the presence of permanent magnets, or it will erase everything because it turns everything to ones or everything to zeros and corrupts your data, okay? So one other thing that I want to talk about with this graph really quickly is that in general, the width of the hysteresis curve, so how wide it is larger at high frequencies and smaller at low frequencies. So for 50 and 60 hertz, which are the excitation frequencies used in the United States and other places, we shouldn't expect to see it be particularly wide. We can largely treat it like the DC magnetization curve. But if we're looking at very high frequency applications, this is going to come into play a lot. All right. So any questions on magnetization curves or anything like that before we move along? All right, so when we work an example problem here in a bit, we're actually going to read this magnetization curve instead of me just giving you a particular value of the relative permeability, and then we'll go from there. All right, so the next thing that I want to talk about is magnetic core losses. So whenever a magnetic material is subjected to a time varying flux, the material will experience energy losses that are typically called core losses. So if we have a DC current, core losses aren't a problem. If we have an AC current, core losses will absolutely be a problem. Typically, these losses can be attributed to two different phenomenon, hysteresis losses and eddy current losses. So let's talk first about hysteresis losses. Okay. So as we discussed a little while ago, when a magnetic material is subjected to an external magnetic field, the domains of the material tend to align with the direction of the applied field. It takes energy to cause those domain fields to rotate into the direction. That energy is the hysteresis loss. Effectively, the hysteresis loss is the area inside of this funny looking curve, okay? Mathematically, hysteresis loss can be estimated using the following equation: V multiplied by F multiplied by KH multiplied by B max to the nth power, and these losses are measured in watts, where V is our core volume. So the total volume of core material that the flux passes through, measured in meters cubed. F is our excitation frequency, measured in hertz. So if we have a current carrying wire wrapped around our core here in the US, it's probably 60 hertz, unless we do something to step that frequency up. KH is going to be our hysteresis proportionality constant. For the particular core material. So this is typically significantly smaller than 1, on the order of 0.025 all the way down to 0.00001, depending on the material. B max is the maximum magnetic flux density in the core measured in Tesla. And N is the Steinmetz exponent. And it is typically 1.5 to 2.5, depending on the material. We will assume that N is equal to 2 if we don't know the value. So 2.0 is a good place to start estimating the behavior in the middle of the range. Okay. So hysteresis losses are caused by the constant changing of the direction of the magnetic field of the domain. Okay. So that'll be a good theory type question for me to throw on you guys as first test. What are hysteresis losses caused by? That kind of thing. All right. Our second loss that we're going to talk about today is eddy current losses. Okay. Or eddy current loss, let's call it that. All right, so what do you guys know about Faraday's law of induction? Not much. Okay, that's perfectly fine. We're going to talk about it much more in depth on Thursday. But for right now, all I need you guys to understand is that Faraday's law of induction says that if you put a conductor in a time-varying magnetic field, a voltage and current will be induced on the conductor. Okay, you guys can actually see this in action if you watch shows like How It's Made and all that kind of good stuff. They'll pass a piece of magnetic, piece of metal material through a current carrying coil, and you'll see that the material starts to glow white hot after a couple of seconds. They use that in aluminum foundries and all that kind of good stuff. You can actually see it, Faraday's law in action, if you have a hair dryer or something like that and turn it on and then pull the plug out of the wall. You'll see arcing and all that kind of stuff. That's Faraday's law of induction in action, where it's generated a EMF in response to the abrupt change in flux so large that it's ionizing the air particles to try to keep that flux constant. Okay, so it's happening all around us anytime we have conducting materials in the presence of magnetic fields, right? So let me draw a picture of a core here. So let's say that we have a core with a square cross section like so. And we wrap a wire around said core, and our wire is carrying some time varying current I of t in this direction. I think that's enough for me. And then our current is going to exit over here. So using the right hand rule, you guys tell me what direction our flux should be in. So if the face of the core is pointed at me and I use my right hand rule, if my current is curling around like this, I would argue that it should be coming out of the page, the direction of my thumb, right? So let's say that this marker in my hand right here represents our core material, okay? If my coil is wrapped around my core such that the current is following the curl in my fingers, the magnetic flux should be traveling in the direction of my thumb. That's what the right hand rule tells us. So this core is directed out of the board, and the current is flowing around it in what looks to me like a counterclockwise direction. So we should see that our flux comes out. Okay. So I'm going to draw my flux line something like this. So this is the magnetic flux caused by my coil will be directed out like so. Okay. Well, since we have a time varying current, we have a time varying flux. Okay. So what Faraday's law and another thing called Lenz's law, and again, we're going to talk about this in much more detail on Thursday, state is that there is going to be a current induced in our conductive medium, our core here, such that the flux introduced by induction will try to keep the magnetic, the magnetic flux constant. So if our coil flux is increasing, our induced flux will try to decrease the overall flux. If our coil flux is decreasing, our induced flux will try to increase the overall flux. The induced flux is just trying to keep the flux constant at a constant level, okay? So if we have currents circulating in a clockwise direction, we're going to find that we have eddy currents, if we have currents circulating in a counterclockwise direction, we're going to find that we have eddy currents induced in a counterclockwise. Damn it. They're going to be opposite to each other. I keep saying it backwards. Sorry about that. So something like this, and I apologize for my inability to draw a circle orthogram. Okay. So all of those eddy currents are going to generate a flux into core. All right, let me erase these things here because I haven't been using that symbol. I think I've been using this one. All right, so what can we do to reduce the presence of eddy currents? Anybody heard this before? So it does have something to do with insulation, but the problem isn't that the wire is touching the core material, because we are assuming here that the wire is kind of insulated already. It's the field that's inducing the current inside it. So the strength of the eddy current, and therefore the strength of the magnetic flux caused by the eddy currents, is proportional to the amount of material that you're passing the flux through. So what we do in practice is we laminate our cores. We slice them up into thin little strips and then effectively glue them all together, and each strip is separated by an oxide or some thin insulating layer. Okay, so we should have something. Let me draw it down here. Yes. I was trying to find an old transformer in Nethkin that I could bring to class today, but all of them had a metal casing around the core, so you couldn't actually see the slices. So let's say that we make some vertical slices like this. These slices are called laminations. And then we wrap our wire around our core. like so. So let's say that I is flowing in this direction. What we're going to wind up seeing is that we have smaller eddy current loops and therefore smaller amounts of eddy current. Okay. So one thing that I want to talk about here before we work an example problem is that this practice effectively reduces the cross-sectional area of the core, because not all of the core is made out of magnetic material now. It's some slightly smaller amount. So we might see what's called a stacking fraction of something like 90% or 95%, and all that means is 90 or 95% of the core is magnetic material. The remainder percentage is the insulator material. Okay. All right, so mathematically, everything worked out okay. Our eddy current losses are given by P sub E, where this is V, still our volume, KE, we'll talk about that in a moment. F is still our excitation frequency. We're going to have TL, talk about that in a moment. Vmax, we square this whole thing, and our power is measured as per usual in watts. In this case, KE is our eddy current proportionality constant. And TL is our lamination thickness. So from this equation, actually, we can see that the thinner that we cut our laminations, the lower the eddy current losses will be. So we want as thin of a plate as we can achieve and as many stacks as possible effectively in order to lower our eddy current losses. All right. So we're going to talk about it in this next example problem. So if we had effectively a solid core material, it would require slightly less current. We're experiencing some small amount of loss, right? One thing that I do want to talk about here, just very briefly, in this class, we're going to view eddy currents as, generally speaking, a pretty bad thing, but in practice, they're quite useful, okay? Eddy currents are how train brakes work. Effectively, a magnetic flux, time-varying magnetic flux is passed through the wheel of a train because they're typically a big cast iron plate. That flux induces a current, which causes the plate to heat up, and that heating up causes the train itself to lose energy and gradually slow down. So it's how you get very soft deceleration instead of a hard braking in a train. It's also used, as I mentioned before, in a lot of metal foundries to heat up metallic or conductive objects. And some of you or your parents more likely have cooktops. Induction cooktops use eddy currents in order to heat the pan up. So very, very practical stuff, but in a magnetic circuit, generally pretty bad. So, all right, so the last thing that I want to talk about today is this example problem. Okay. So this is the hardest difficulty of thing that I could potentially ask you guys to do for homework or test, okay? So the magnetic core shown below is made of M 1929 gauge steel sheets with a stacking factor of F stack is equal to 0.90. Now I'm going to draw our core. So we have some core with an air gap. Let's throw some dimensions on this bad boy. Let's say that this is W, this is W, this is W, this is also W. This length right here will be L2. This length right here will be L1. This length will be LG, where L1 is 10 centimeters. L2 will be 15 centimeters. LG will be 2 millimeters. Our width is 1 centimeter. And our thickness is also 1 centimeter. And we're going to apply our coil over here. Like so. And what I want us to do is to estimate the required coil MMF needed to produce a maximum flux of phi B is equal to 125 microweber in the, core. Okay. So the reason why I'm saying estimate instead of calculate here is because our answer is going to rely on our ability to read this terrible graph. Okay. So I pulled this one out of the official textbook for our class, blew it up a little bit and all that kind of stuff, and it came out a bit fuzzy. For your exams and things like that, I will produce custom graphs for made up materials that will be much nicer and easier to read for your benefit. I'll try to do something like that for your homework as well. Okay. All right. So effectively, we have something similar to what we've dealt with before. We're trying to find the MMF needed to produce a flux. The principal difference that we have here versus the work that we've done before is that we don't know what the permeability of the material is. So we're going to have to figure that out using our BH curve. And we have a stacking factor, which we have yet to use before. Okay. So let's start by addressing the stacking factor problem. Okay. So the nominal cross-sectional area for our core is just going to be the width of our core times the thickness of our core, because that's the cross-sectional area that our flux would see if we hadn't sliced our core up into some number of laminations, right? how we are going to incorporate our stacking factor is simply by multiplying our core area times the stacking factor, which tells us how much of our core cross-section is actually magnetic material, right? So we can say that, let's call this AC actual is going to be W times T times F stacking, or 1 centimeter times 1 centimeter times 0.9. Looks to me like 0.9 centimeters squared. Anybody have a problem with that? Hopefully that's pretty straightforward, all right? So now let's talk about how we're going to utilize this table, okay? So our table has flux density B on the vertical axis and magnetizing intensity H on the horizontal axis, okay? We were told a specific amount of magnetic flux, phi B, 125 microwebers, okay? So our actual value of the magnetic flux density in our core will be phi B, our flux, divided by AC actual. So that's going to be 125 microwebers divided by 0.9 centimeters squared. And this will come out to be 1.389 Tesla. So now what we have to do is figure out which value of H corresponds to that value of B. Casey. Right there. Yep, in the problem statement. So what I did on my graph here is I called 1.389 Tesla about 1.4 Tesla, and then I drew a horizontal line, and then I figured out where that horizontal line intersected my magnetization curve for M1929 gauge steel. And to me, that looked to be about 1100 amp turns per meter. Okay, so that's what I got from the table. Because it's so fuzzy and stuff, I literally had to use a damn ruler to do it, but that's what I got. Okay, so hopefully you guys can do it a little bit easier in yourselves in the in-class assignment, because that's going to use the table on the back, which isn't quite as garbage to read. Okay, so our magnetizing intensity for our core, I'm going to call it 1100 amp turns. That looks like amp tums, so let me fix that, per meter. And I'm going to write here specifically from graph. We read it off of the graph, okay? From this, I can say that mu for my core material, so let's call this mu C, is simply going to be the ratio of our magnetic flux density divided by our magnetizing intensity. 1.389 Tesla divided by 1100 amp turns per meter. And this is going to give me a value of 1.263 times 10 to the minus 5 henries per centimeter, where I've done some unit conversions there to put it in the form that we are used to seeing. As it turns out, 1.263 times 10 to the minus 5 henries per centimeter is about 1,000 times larger than mu naught. So effectively, at this point along its magnetization curve, M1929 gauge steel's permeability is about 1,000 times larger than mu naught. If we were somewhere in the linear portion instead of the knee, it would likely be much, much higher. Okay. All right, so at this point, we're effectively ready to treat it like every other magnetic circuit that we've worked. If we want to know the MMF required to maintain that flux, we're going to need to know the equivalent reactance. The equivalent reactance, or excuse me, reluctance. The equivalent reluctance multiplied by the flux gives us our MMF that we're looking for. So we have a core that we need to worry about its reluctance and an air gap that we need to worry about its reluctance of. So let's start with our core. And let's look at the left-hand portion of it first, okay? So that leftmost leg has a length of, or a flux path length of what? L1 minus W, absolutely right. So this is the boring stuff where I've beaten this to death. So R left is L1 minus W, and it's going to be divided by mu C times AC actual, right? So that's going to look like 10 centimeters minus 1 centimeter divided by 1.263 times 10 to the minus 5 henries per centimeter times our cross-sectional area of 0.9 centimeters squared, giving us a reluctance of 7.920 times 10 to the 5 amp. I don't know why I can't write the word turns today. Amp turns per Weber. Our top and bottom flux paths are going to have the same reluctance. So what's the average length of the flux path for that part? L2 minus W. Yep, pretty straightforward. And to save us both some time, I'm not going to put numbers into this equation because you guys know how to do that simple substitution because we beat it to death. You get a value of 1.232 times 10 to the 6 amp turns per Weber. Then we have the right-hand side, which is going to have a length of L1 minus W minus the length of the air gap over mu C AC actual, which comes out to be 7.744 times 10 to the 5 amp turns per Weber. And our core reluctance is then R left plus twice R top plus R right, which I got to be 4.030 times 10 to the 6 amp turns per Weber. Now we have our air gap to take into account. So for our air gap, our length is just going to be LG. Our permeability is mu naught because we don't have the ferromagnetic material to deal with, it's just air. And then our cross-sectional area that we see, recall from our last class that we simply add the length of the air gap to the width and we add the length of the air gap to the thickness. So this is going to look like W plus LG times, T plus LG. And if I substitute numbers into this, I got 1.105 times 10 to the 7. Amp turns per Weber. And from this, I can say that my MMF is going to be flux times my reluctance. So this is going to be the reluctance of the core in series with the reluctance of the air gap. And I get a MMF of 1,855.353 amp turn. So that's how much MMF I need to supply. Oh God, it's doing it again. All right, my computer is about to die again, Hugh. I'm very sorry. I will get this fixed later, but I was finished anyway. So see you later.